Having come to this point in the course, we've accumulated a lot of tools, a lot of individual ways to code various things. But if I asked you right now to write some larger program, like one that keeps track of storing and retrieving sales orders, or one that analyzes historic weather data to give average daily reports, or one that lets you play a game, any of those might seem rather overwhelming, and they probably should. Just like there's a difference between knowing how to use a saw and hammer and knowing how to build a piece of furniture, there's also a difference between knowing how to use the individual programming tools and knowing how to bring them together to create something larger. So, in this lecture, we're going to talk about some useful methods for approaching bigger software problems. There are three main things that I want to go over with you here. The first is the top-down design process. Top-down design helps us decompose a challenging problem into easier to understand pieces. The second topic is incremental development. And we've discussed parts of this before, but as we deal with larger projects, it becomes even more important. And finally, I want to introduce you to the Debugger tool provided in an IDE, your integrated development environment, like Visual Studio or Xcode. As you work to develop larger programs, having the use of an IDE can be critical to helping examine the state of the program as it progresses, and that helps you make sure that the program's working as intended. So, let's talk about top-down design. Top-down design is a process we almost all follow, often unconsciously, when we're going through our everyday life. The basic idea of top-down design is that you take a big task and you break it into a sequence of smaller tasks. And then you take those and break them into a sequence of yet smaller tasks, and so forth. If I asked someone how they spent their evening, they might say something like, "I drove home, fixed dinner, got the kids to bed, and went to sleep." They've broken the larger task of spend an evening into a series of smaller tasks, like driving home, getting kids to bed, and so on. Now, we could ask the same thing about any one of those smaller tasks, like, how did you drive home? And in that case, we might get a new set of even smaller tasks. I drove south on Oak Street and then took the highway up to exit 73 and then drove down Main Street to my house. And if we kept asking, how did you, we might eventually have them telling us that they were applying more pressure to a gas pedal or pushing down on the turn signal lever. Now, what if I had asked someone, how did you spend your evening? And the answer I got was, I went out the back door of the building, I walked across the parking lot to my car, I unlocked the car using my remote, and so on. Well, that's the pitfall for many beginners approaching a software problem. If I said, how would you write a program to calculate mortgage interest payments, you should not respond, first I would pound include IOStream, then I would pound include string, then I would pound include CMath. Of course, you need to know those lines, but starting there when approaching a problem is like being asked how you spend an evening and immediately jumping to a discussion of how you unlock your car. And yet, that's what beginning programmers often do. They'll have a programming task ahead of themselves and will want to jump right into writing individual lines of code, the smallest unit of code there is. Instead, we need to treat programming tasks similar to the way we treat other tasks. First, we need to consider the problem as a whole and try to break it down into conceptually simpler parts. And eventually, we get down to individual lines of code. But at first, you don't need to think about all the details of the code, just the overall steps to follow. Now, the question we face when performing top-down design is exactly how to break up our task. Now, in computer science, we give a particular name for this hierarchical structure, and it ends up being useful in lots of programming applications. So I'm going to introduce that terminology here. The term we use for the whole hierarchy is a tree. The individual elements in the tree are called nodes. We refer to the single node at the top of the tree as the root. And if two nodes are connected, then the one closer to the root is the parent, and the ones farther away are the children. Every node, except the root, has exactly one parent, but it can have several children. For a parent, we say that the children and all of their children are branches. The nodes that don't have any children are called leaf nodes. And finally, we call the number of levels in the tree the depth of the tree. And the average number of children that non-leaf nodes have is the branching ratio. So, as we think of the design process, that's how we take a problem and we decompose it into a hierarchy. we're often concerned with two questions. How deep do we want the tree to be, and what branching ratio do we want? Thinking of this in terms of an organization, the questions would be, how many levels of management do we want between the employees and the leader? And how many people should generally be directly reporting to each person in management? Well, in software development, we have the same kind of questions, but there's not a single answer to either one. Instead, there are two rules of thumb. First, the branching ratio, that's the average number of children per node, should not be so high that we can't understand all of the children of one node. In other words, one task should be broken up into a few subparts so that it's easy to understand how the larger task is broken into the smaller ones. Second, the depth, the number of levels in the tree, should be deep enough that the leaf nodes are obvious. Now, by obvious, we mean that a particular task should be something that an experienced programmer could readily implement without having to understand the other parts of the program. Typically, this means just a few lines of code. One more point about the general process of top-down design. There's never just a single correct answer. It's possible to break down any reasonably complicated task in multiple ways. For instance, companies organize their management structures differently. Some will organize based on the general role that people have, accounting, HR, and so on. Others will organize based on geography, or product groups, or whatever. Likewise, in software development, there's always more than one way to write a program. There's never only one option. And while some ways of solving a programming problem are clearly better or worse than others, there's rarely any one way that's truly ideal in every regard. Different approaches to the same problem can have different results. So, let's practice doing this for a simple problem. Imagine that you've been asked to create a program to predict electricity usage at someone's house. And you have files available with data about past electricity usage, as well as weather data and information about the person's schedule. And you want to get a sense of what to expect regarding future energy demand. Now, if I told you to go write that program, it probably seems daunting, to say the least. But let's use a top-down approach to it. First, let's think of the major steps that we'll want to go through. We'll want to read in information from the data files that we have. We'll want to get some information about exactly what we want to predict, such as the range of dates. And we'll want to do our calculation to actually make that prediction. And we'll want to output some results. Now notice that any one step is pretty simple, and that's the point. For any one idea, breaking it down into simpler ideas shouldn't be too hard. Then you can turn to each of those subtasks that we just identified and expand them. So let's take the first subtask, reading the past data. For this, we have information about past electricity usage, past weather data, and past schedule. So we'll want to read in the data from each of those files. Okay, what are the steps involved in reading a file? Now we go on to take each of our current items and we break those down. So reading the electric usage file will depend on how it's stored. Let's assume that the data is stored in a series of lines, each one with a date and an electric meter reading. The basic process that we'll want to follow is to open the file, read in each line, and then store the data, in this case in parallel vectors, one for the date and one for the meter reading. And we keep going until we reach a level that should be pretty straightforward to code. So here, each of our tasks corresponds to just one or a few lines of code. Now you could continue to walk through the entire program at this level of detail for each part. But here's the idea that I hope is getting across. What starts out as a daunting task becomes more manageable when it's broken down into simpler and simpler pieces. And once we have the program decomposed with a top-down design like this, then we can begin to code it. So to get started, this is a great point to take the pseudocode that we've been generating and convert each step into a comment, generating comments for each of the sections that we've described. These comments will help guide our code, and they provide an explanation for the purpose of each part of the code, both during and after writing the code itself. Now, considering our hierarchy, the root node becomes the overall comment for the program. The next level, the children of the root, should each get their own comment. Since these are at the higher levels of the hierarchy, it can make sense to designate these in some way that makes them especially stand out. So in this example, I've used several asterisks to make them stand out a bit more since they'll be major sections. Then we can divide those into the next level down. Again, we convert each node into a new comment. In this case, I again used a few asterisks to show that these are not the most basic levels of the hierarchy. And then we can go from there to even the next level down, converting those nodes to comments. And each of these is still pretty self-explanatory. Once we've done this for our whole program, it's time to start writing code. Now this leads me into the second main thing that I wanted to talk about regarding developing large software projects. That's incremental construction. So to describe this, I want to use one of my favorite analogies. It's one I tell at some point to almost all of my classes, from the introductory programming to graduate level classes. I think it applies very well to software construction, and so I'm going to share it with you. Here's the analogy. There are two particularly long-lasting and strong architectural structures. Those are the pyramid and the arch. We have examples of arches still standing from their construction 2,000 years ago. And we have pyramids going back even further. Both of these make interesting structures in the end. But the way that they're constructed is very different. With a pyramid, every block gets placed on top of other blocks. And its stability comes from resting on top of the other blocks that are already in place, and adding another block gets us a little bit closer to the final product. Now, most importantly for this analogy, if something happens at any point in time and we have to leave the pyramid alone, everything that we've put down will still be standing. We have a nice stable structure at every point in time. Even a partially constructed pyramid is still going to be nice and stable. Now, on the other hand, with the arch, the stability of the structure depends on every stone being put into place. During construction, the only way the structure is held in place is with temporary scaffolding. And only after every block is positioned in place is the structure a stable one. So here's the analogy to software development. When we develop software, we want to build it like a pyramid, not like an arch. We want to construct the software piece by piece, and as each piece is put into place, we want to ensure that we have a stable structure, something not yet complete, but something that will operate just fine for the part that's been written. We want to be able to see that each piece works and gets tested as we go along. And if we ever write something that's not working, we can always take one step back and be at a nice stable piece of software. Now, unfortunately, many times I see students, even very experienced ones, construct a larger piece of software, and instead of following a pyramid style of building, they'll follow an arch style. They'll write lots of code, and only at the end, after they think they have all the pieces in place, do they try to test it. And if everything actually works, it's glorious. But it's very rare for that to happen. Instead, somewhere along the way, they made a mistake, and then the entire program falls apart. Now, trying to find that one mistake is difficult, and sometimes even after fixing that, there's another mistake, and they can't even figure out if they really fixed the first problem or not. So, what pyramid-style construction means is that we use an incremental construction approach. We code a little, test it, till we're confident that everything to that point is working, code a little bit more, test again, and so forth. We never move on until we're confident in what we already have. Now, unfortunately, that's easier to say than to really do. It's easy to get so excited writing new code that you don't want to stop and run tests. But if you don't, you'll almost certainly regret it eventually, when the arch that you were attempting to build falls apart. Incremental development is a critical part of developing larger software programs, and it's almost impossible to develop large programs without it. So, back to our coding example. It's okay to design our entire program top-down and write out the comments for each part ahead of time. But when it comes to coding, we want to write code in a way that we can implement a small chunk of the program and test what we've written. Generally, this means that we'll have to write code in a sequential order, though once we start writing functions, that won't have to be the case exactly. In our example from before, the first section we encounter is part of reading past data, where first we'll read the past electricity data, and where the first part of that is opening the file. And that means that we declare an fstream variable and then open it for input. Notice that we also write a line of code to close the file. We know that we need to close any file we open, so we write it there. Now, after writing this, before going on to the next section, we want to stop and test what we have, making sure that we don't have a typo or some statement formatted incorrectly. Okay, so once that's tested, it's time to write and check our next section, looping through all the lines of the program. In this case, we'll assume that the file consists of lines, each of which is a date given by a string and a meter reading given by an integer. So, to loop through all the lines in the file, we'll need to have two variables, which I've labeled date and meter. We'll try to read them in from the file and loop until we've reached the end of the file. And inside the loop, we'll read the next line. Now, also inside the loop, we'll have what we want to happen each time, which is to add the date and the meter reading to vectors. But we're not going to write that part yet. We don't want to go build arches. Let's stick with the pyramid approach. We want to test what we have so far. Now, how do you think we could test this? We want to test that we're reading in all the lines from the file. Well, we could put in some output statements to show what we read in from each line, and that's better than nothing. But there's another option we have available, using the debugger. And using the debugger is the third and final key that I wanted to mention as being useful for building large software. Now, to use the debugger, you'll want to have an IDE like Visual Studio, making it easy to access and use the debugger. There are other debuggers. For instance, GDB is used in Linux from the command line. But by far the easiest to use are those included in an integrated development environment. I'll demonstrate the one in Visual Studio here. First, let me say a word about what a debugger really is. Unfortunately, it is not a tool that takes the bugs out of your program. That would be awesome. No, a debugger is a tool that lets you step through a program's instructions, one at a time, and examine the state of everything in the program at that point. Debuggers have a lot of tools within them that can help a developer examine their code very closely. But for now, there are just a few simple parts that I want to explain. They're enough to make the debugger a really useful tool. And even if you knew every feature of the debugger, these would still account for 90% of what you'd ever do. The features are breakpoints, the step over and step into operations, and examining the variable values. We're going to demonstrate debugging on a small program to make it easier to illustrate. The program is a very basic one that just outputs a few lines and numbers. In order to use a debugger, the code must be compiled in what's called debug mode. That mode adds some extra stuff in automatically that lets the debugger work, though it also makes the code less efficient than it will be when fully debugged and then compiled into a more efficient form called release mode. Now, because most development is done in debug mode, that's the default mode for compiling in both Visual Studio and Xcode. And when the code is executed, it's usually run through the debugger. You don't have to do anything special to compile in debug mode, and to run the code in the debugger just means you use the default run. In Visual Studio, that's called start debugging, rather than the alternative start without debugging. In other words, to run the program in the debugger, just do exactly what you've been doing. Okay, the first thing I want to mention is a breakpoint. A breakpoint is a point in the code at which you want to stop the execution, usually so that you can examine the code more closely. When you run a program in the debugger, it'll run just like you'd expect until you hit a breakpoint. The execution will pause just before the line where the breakpoint is set. The breakpoint is a break, not a line that's already been executed. If you don't have a breakpoint set, the code will just run all the way through, and that's what you've been seeing until now. In Visual Studio, to set a breakpoint, you click on the area farthest to the left edge for the line where you want to stop. I'll set a breakpoint at the very first cout statement, and this puts a red circle there at that line. In Xcode, it's very similar. You click on the thin vertical area just left of the line of code, and a blue marker appears to show the breakpoint. Again, this means that the program will pause there before it executes the breakpoint line. Let's go ahead now and run the program and see what happens. The program will run and then get to the breakpoint and stop. There will be a visual indicator showing which line of code will be the next to execute. It's a yellow area on top of the red circle in Visual Studio, or a highlighted green line in Xcode. In this case, we're stopping before any lines of output were executed. Let's set a second breakpoint, a few lines later, at the third cout statement. Now, if we hit continue at this point, the program will continue executing until it hits that next breakpoint. In Xcode, the continue button is a less prominent rightward-facing hollow arrow down below the code. Notice that the indicator shows that we're now at this new line where we just set the breakpoint. Also notice that in the output area of the IDE, we see two lines that have been output. The first two cout statements were executed. That's one way to go through the program, to set breakpoints and continue running between them. But once you've reached a point of interest in the code, you often want to examine just one line at a time. Putting a breakpoint on every line would be one way to do this, but that's really overkill. So let's look at a way that we can progress through the code line by line using a command called step over. Right now, the next line to be executed is the third cout statement. In Visual Studio, there's a button up near the top called step over. In Xcode, a step over button is at the bottom, next to the continue button. Either way, if we push the step over button, notice that the marker showing which line we're about to execute progresses to the next executable line, the for statement. The third line was output. If we step over again, we're inside the for loop. One more step over, and we print the I value and go back to the top of the for loop, where we check the conditional. And we can keep stepping through. You'll notice that we go through all iterations of our loop, and eventually we leave once the loop condition is false. Now, to stop our debugging session, we can hit the square stop button. That will stop the entire run. Also, you may have noticed as you clicked on some of these buttons that there are often keyboard shortcuts for them. For instance, to start debugging, you can hit F5 on a Windows machine or Command R on a Mac. The step over command is F10 on a Windows machine or F6 on a Mac. If you prefer to use keyboard commands instead of the graphical interface, that's fine. Besides the step over command to step over the next line of code, there's a step into command. Starting in the next lecture, we're going to see how to write our own functions. Step into doesn't just say, execute the next line of code. If that next line of code has a function call in it, then the execution goes into that function. That way, you'll be able to see how the function itself is working. There's also a step out button if you're tired of looking inside a function's inner workings and you want to return to the place that it was called. So, keep in mind that the step into option is right there with the step over option. Okay, there's one other key part of the debugger, and it's a part you might have already noticed. When the debugger runs, there's a window at the bottom that lets you examine the values of variables. Let's see how it works. Let's go back to our electric usage program. Let's put a breakpoint right before the first line where we stream in from electric file. Then let's start the debugger. It will execute right up to that line. Now, look at the bottom of the screen. You should see a window at the bottom that shows variable values. In Visual Studio, it will have tabs, and one of them, probably locals, will be selected. You should see 3 items listed there. In alphabetical order, they're the 3 variables that we have at this point in the program. The first one is date, the second one is electric file, and the third one is meter. Now, next to each of them is the value of that variable. Notice that neither date nor meter was initialized to anything. The date should have an empty string as its value, while the meter could have any possible number. We haven't read anything into either one of them yet. The variable electric file doesn't have a very meaningful value. It's reporting on how an fstream is implemented. If we go forward one line by pressing step over, we move on to the next line of the code. We also see that the values in both date and meter have been updated. The previous line read data into both of them from the file. In this case, we have a date of January 1st, 2018, and a meter reading of 1024. As we go through the code, we can keep an eye on the window to see what the values of variables are. One other useful item in the debugger is a call stack. In Visual Studio, the call stack is found in the lower right, and in Xcode, it's in the lower left, where there's a window showing the call stack or thread. If you have written your own functions and stepped into those, then the call stack will also show which functions have been called in order from other functions. And in Visual Studio, the call stack also shows the line numbers. Now, stepping back to remember the bigger picture, the whole reason that we're using the debugger here is to verify that our code is working as expected. We can run through the code and verify that indeed we're reading in the lines of the input file, getting the date and meter reading for each line. And assuming that we know how large the input file is, we can verify that we get to the end of it, and that the last thing we read in was the last line. The debugger will be very useful for us when we do encounter bugs and need to find out where they're occurring. But it's also useful in verifying that our code is working as we develop it. It's our way of making sure that every block that we place in the pyramid is stable before we go on to place the next block. Now, at this point, we could go through and expand on the entire program I've started here. First, completing the full top-down design of the entire program, then incrementally building every piece of it, showing how to read from every file, set up every variable, perform every computation, and so forth. But what's more important here, the lesson to take from what I've been demonstrating, is a systematic way to approach a larger, more complex problem for yourself. Start with a top-down design. Then build it incrementally. And use the debugger to help you verify that things are working. Developing large software programs is a challenge, and we're going to want more tools to help us manage complexity. One of these will be functions, which will be the topic of the next couple of lectures. Another will be object-oriented design, which we'll get to later. At some point, projects get so large that multiple people need to work on them, and that opens a whole new host of issues. But in all cases, the principles that we've talked about here, top-down design, incremental pyramid-style development, and use of a debugger will continue to be useful. In our next lecture, we'll see how to solve more complex challenges by learning how to write our own functions. See you then.